Heyo, what's up guys? Baby Bear 4812 coming at you once again. Today we're going to be solving the famous or perhaps infamous search and rotated sorted array problem. Now this one's being asked by, we got Facebook, Amazon, Bloomberg, Google, the whole nine. Everyone's asking it. You got to know it. That's why I wanted to cover it. It's a very important question, and again, like most of the ones, and I kind of find myself saying this every time, I don't think it's trivial. I really don't. Basically, if you're not familiar with it, the question states that we are given an integer array nums sorted in ascending order. Okay, this is going to be important. Sorted in ascending order and an integer target. Suppose that nums is rotated at some point or some pivot unknown to you beforehand. For instance, 0, 1, 2, 4, 5, 6, 7 might become 4, 5, 6, 7, 0, 1, 2. If target is found in the array, return its index. Otherwise, return -1. For example, if we have 4, 5, 6, 7, 0, 1, 2, we take a look and we say, is 0 in there? Well, we can walk through and the answer is yes, so we return its index, which is 4. If we look for 3, on the other hand, it's not in there, we would return a -1. Simple enough. A few constraints here on kind of size. It says that the values are unique, which makes your lives a bit easier, and nums is guaranteed to be rotated at some pivot. Now, I know what some of you are all thinking. This could be super trivial. We can do it in linear time, constant space. Let's just do a walkthrough. If we find it, we find it. If not, let's not. So it's something as simple as for I and num and enumerate, say nums, what we would just do is we could say if num is equal to target, we could return I. Otherwise, if all that doesn't work, we return -1. That would work, but please don't do this in the interview. You would be severely undermining what we're trying to get at here in this problem, which is actually that we can solve this in logarithmic time. If you haven't tried it yet, I'd encourage you to pause the video, as always, my laptop's in the way, to give it a shot and to see if you can come up with the logarithmic solution. Pause it, come on right back if you get stuck. And so the answer, obviously, like I said, is we will be able to do this in logarithmic time, and we need to think about why. So let's kind of go over to our sketch pad here, and I'm going to use this example here. So we had 0, 1, 2, 4. Oh boy, 0, 1, 2, 4 as our array. Oh yikes, I'm having issues here. 0, 1, 2, 4, 5, 6, 7. Let's say that the question asks, is the number 4, is the number 6 in this array? We could find that, sure, in linear time with a walkthrough, but if the array is sorted, then the sorting is actually the prerequisite for us to be able to use a divide and conquer approach. And specifically, what I'm referring to is like a binary search. What we could do is we could simply say, and if you're not familiar with kind of binary searches, I would pause the video, go back and brush up on those before we kind of keep going here, because it might be a bit tricky to follow along. But we could do something like, let's set a left pointer and a right pointer here, and then we calculate a midpoint. Midpoint would be here. And then we ask ourselves, well, the number we're looking for is 6. Is 6 greater than the midpoint, or is it smaller than the midpoint? In this case, it's greater than. So what we do is we would limit our search to now this array. We would set our left pointer over here. We'd get a mid pointer here, and then oh look, our mid pointer happens to fall on a 6. And this is actually exponentially quicker than doing the linear search. And in fact, the difference between going from log of n to n, or in terms of speed or time complexity, is the same as going from n to 2 to the n. So it's an incredibly big difference, and as our arrays get super large, then this does make a very material difference, which is why we have to take this into account. Now, the issues with this problem is that we are not given an array that's sorted this way. Rather, we're given this array that's pivoted by some amount, and the sorting exists almost in 2 chunks. And so I think the example they gave here was 5, 6, 7, 0, 1, 2. So really, this becomes long day. 4, 5, 6, 7, 0, 1, 2. So imagine this array was kind of rotated by a few positions. Maybe we took these and moved 3 units to the left and kind of shifted everything over this way. Oh, so I think you get the picture there. Now, this makes it more complicated. So now the question is like, well, where do I search from? If I want to do a binary search, I can't. If I simply went, well, let me do left and right and calculate my midpoint here. Like, which side do I look from? Like, where do we? At this point, sure, we're increasing at one point, but then we stop and we drop back down, and then we're increasing again. And so, do I search on the left? Do I search on the right? How do I actually go about making my decision on which way to split up my array into chunks? And that's what we're going to be addressing, because, like I said, I don't think it's obvious whatsoever. The key here to understand is this array, in a sense, is still kind of sorted, and I alluded to this earlier, but it's sorted in 2 different ascending chunks. This right over here is one chunk of array that is sorted in kind of on an increasing ascending way. It goes 4, 5, 6, 7. Second chunk is right here, 0, 1, and 2, which is also increasing steadily. These 2 sides they're sorted individually of each other. The key here to actually be able to do this in binary search is before we stop and do that divide and conquer and do the binary search itself, our step 1 is going to be, so it's going to be step 1 is going to be find the pivot. If we can find the pivot, if I can find that, okay, I'm kind of pivoting from this point here, this is 0 has been shifted over by some number of units, maybe either to the right by 4 units or to the left by 3, whichever way you want to visualize it. Well, if I can compare my pivot point to the end of the array, then I can ask myself, do I look to the right half or do I look to the left half? Okay, and that's the important part. We first need to find the pivot. Once we identify the pivot, we can then say, do I want to binary search on this half or on this half? And so let's say we've identified the pivot as right here. 0 is our pivot. If the number that I'm looking for, let's say the target that I'm looking for, I'll denote with T, is a 6. Okay, now we ask ourselves, if I'm looking for a 6 and my pivot is 0 here, should I look on the right half of the array or should I look on the left half? Intuitively, we can look at this and say, okay, well, 0 is kind of my starting point, and to the far right, to the far extreme of this is a 2. I know that from my pivot to the end, I am increasing because that chunk, like I said earlier, is strictly increasing and is sorted. If I compare my 0 and my 2, is 6, is it greater than 0 and less than the setting point 2? No, it is not. So that means that this goes bye-bye Charlie, and we are now focusing on the left half of the array, which is where we are going to do our standard binary search for this number. And as you'll see, we will find this number here, 6. This would still work even if we said, let's say the target was 3. I could ask myself the same question. Well, 3 would not fall into this range. However, it could potentially, if it's not going to fall into this range, we must then check the other range. We check this other range, and as we walk through it, we notice, oh damn, 3 isn't really in here, so we're going to return a -1 at the end of the day. So step 1 is find the pivot, and then step 2 is going to be maybe search, let's say binary search the appropriate half, as in half of the appropriate half of the array, or the appropriate section of it. I hope that makes sense. So we will, as always, kind of do a full walkthrough of the code and build it out, but I wanted to build the intuition behind how we're going to approach this, because this trips a lot of people up. But as you saw, this got 5,500 likes. The companies, once again, are here. You can take a look for yourself. This is an important question, and I want to make sure that when you guys get it in your interview, you're going to crush it, you're going to get a high-paying job, and then everybody's happy. All right? So, again, that's the basic intuition, and yeah, let's dive into the code now. So, we're at the point where you got to start coding. So, okay, where do we begin? Well, as always, we like to do our simple error checking, and I'll say something along the lines of it, if not num. So if we get an empty array, we're going to return -1. Next, and I'll kind of make these, so they do tell us here that the target is within a range. We will be given a number. That's always a clarifying question. You can double check with your interviewer as you're working through the problem with them. Now, well, So what did we say we wanted to do? We said that we needed to, first things first, actually find where the pivot is of this array. And so, yep, that's the first thing we're going to do here. The way that I approach this problem is I would just say, I'll name a variable and call it pivot, and I'll say that that pivot point is going to be equal to, what we'll do is we can call a separate function where we're going to find the pivot of nums. For me, I just like to modularize the code. You don't strictly need to do this. We could put this within the body, but I like to just split it apart. So first thing we're going to do is like I said, we'll find our pivot. So we'll define pivot with self and nums as follows. We're going to want to have some left pointer, and we're going to have our right pointer, which is going to point to the end of the array. So it'll be the length of nums minus 1. Now, what we're going to want to do is this: we're going to want to do a standard, almost binary search. So we're going to want to kind of move these pointers along, while the left pointer is smaller than the right pointer. But what we're going to want to do is to say, let's start with the obvious. So let's say that mid is going to be equal to, typically, we could say, just mathematically, if we want to find the average of two numbers, we add the two numbers and we divide them by 2. Problem is, these two numbers are both super big. We could get into an issue, of integer overflow, where the number is way too big to handle. So what we'll do is we can change this to be left plus right minus left divided by 2. Now this subtraction will it'll take away from that issue of the potential integer overflow. The reason this works, by the way, if you're not familiar with it, I would encourage you to write this down and just manipulate the fraction. So kind of write this out, expand the fractions, and see that you're going to end up with right plus left divided by 2. And these two are mathematically equivalent. So now we're going to want to ask ourselves this. So we've got our midpoint. And now we want to know, how does my midpoint compare to the end of the array that I'm looking for? So what we want to ask ourselves is this: is basically, if the midpoint that I'm at, if it's greater than what I've got on the right, then I have not yet found my pivot, and it must be on the right hand side of the array. And what I mean by that is basically this: imagine we were looking at this array action, we found that our midpoint was right here, and we said, we compared 7 and 2, and we said, okay, well 7 is greater than 2, and if that's the case, then my pivot must be somewhere here. It must be on this right hand side of the array. And so what we would do then here in the code is we'd say that if nums of mid was greater than nums on the right hand side, then what we do is we'd have to say, let's only look at the right half of where we are. So we'd say that left is equal to mid plus 1. Otherwise, if that's not the case, we're going to say that right is equal to mid. And so what that means is that if the midpoint is kind of less than or equal to the right hand side, then we must be on the left. And I'm going to take my right pointer and slap it back toward the middle and check the left half of the array. When this is all said and done, this is kind of a typical binary search, so I won't go kind of spend too long into this. We will simply return the left pointer. The right one should work here as well, so whichever one you return works. Just kind of out of habit, I like to return the left one. So let's think of what we've done so far. We've simply gone in here and done our error checking. Now we said, let's find our pivot point. Once we find our pivot point, now we're going to make the decision and say, okay, let me compare where my pivot point stands with respect to the rest of the array, and then I'll do my standard binary search there to try and find the target value that we're provided. So if I go and I say, I want to do my standard binary search, now I'm going to say my left pointer is equal to 0, and my right pointer, I'm just going to say for now, is still equal to the length of nums minus 1, like it kind of was before. There's one thing I'm going to want to check, and the one thing I'm going to want to check, I guess maybe I should say, I just define these so I have the variables defined now, but they will now potentially need to shift around depending on where our pivot was, and what I mean by that is this. So what we're going to want to check now is to see, where does our target fall in this range with respect to the pivot point and our left and right pointers. Basically, what we're curious in is if our target is either greater than, or it's both greater than or equal to nums of the pivot point, and it's less than or equal to nums of right, then we know that we need to search in the right half of the array. Again, the right half of the array, because this number falls somewhere between our pivot and the right hand side. If that's the case, then what we're going to want to do is we're going to have to take our left pointer and set our left pointer equal to pivot. So when we do our binary search, we're only looking at that 1.5. If that's not the case, then we're going to want to set our right side equal to the pivot, and then do a check on the left-hand side of the array. Now from here, it's pretty much business as usual, and what we're going to do is we're going to say, while left is less than, now this one's a bit different, we'll say is less than or equal to right, for the simple reason that if the two of them are equal, we still want to actually check that index to see if it's equal to the target and then return that. Whereas we didn't want that overlap up here when we would get potentially an infinite loop. So while left is less than or equal to right, we'll do the same thing with the mid. I'm going to do the exact same calculation, divided by 2. And now we ask ourselves the following. We ask ourselves first off, if nums of mid is equal to the target, then we're happy campers. We got exactly what we wanted. So we are going to say return mid, and that's about it. We won. We found the number. However, if we haven't found the number, we need to check if our midpoint is greater than the target. If our midpoint is kind of greater than the target, then let's think about it. If it's too big, we want to be checking on the left-hand side of the array. So we're going to say that right would be equal to that midpoint minus 1. Otherwise, what we're going to want to say is we got to check the other side of what we got, which is going to be that left is equal to mid plus 1. And the reason I'm doing plus 1 is because, if we set it equal to mid, then we'd already have in this kind of condition we'll be checking, but we already know that's false. So that's why we're doing that. At the end of all this, we should be able to just return -1 if we haven't found it, because if we did, we would have kind of returned it here. So I'm going to try to run this. Let's just make sure I didn't make any silly errors, which of course I have. I call this pivot instead of find pivot, and so that'll yell at me. If we pass that, let's just make sure that there are no other obvious bugs, and there we go. So that was the search and rotated array problem. That's problem number, I believe it was 33. 33 on Leetcode, super popular. Want to make sure you guys know it. If you have any questions, if anything is unclear, drop it down below in the comments as well. If you enjoy this, found it useful, like, subscribe, share, the whole 9. Really helps me go a long way. And yeah, I want to keep putting out good content for you guys. So anything else you want me to answer, let me know down below, and I'll get to it. See you next time.